Okay, so we've used terms like nucleophile, which what was the rule of thumb? What's a nucleophile going to have? Lone pair electrons. I'm sure there may be, that's like 99.99999% of them. And so they're going to be either negatively charged or delta minus. Okay? And by the way, does anyone know what's the atom that gets attacked by the nucleophile? What is it called? Electrophile, because it loves the electrons coming in. Okay, so then whenever we had our substitution reactions, when things were coming in, things had to pop off, or they had to pop off first. Remember I told the story about the old professor that taught me, and he would punch somebody and talk about their teeth. Well, whatever leaves is called the leaving group. And the generic reaction that we've been talking about for the substitution chapter is we start off with an alkyl halide. We have some type of nucleophile. It comes in, smacks the carbon that it's attached to. Okay, and this leaves. If it happens at the same time, it is called an SN2 reaction. If the leaving group left first to make a carbocation, and then the nucleophile came in, that was called an SN1 reaction. So then we have our product of our substitution, and then we have the inorganic product as well. So the best leaving groups have to do with strong acids. And remember, we've already talked about the fact that strongest acids on the halogens was hydroiodic acid. HI was a much stronger acid than HF. Likewise, you can also think of it with respect to the weaker bonds. This I is so big and fat. Remember that its nucleus was so far away from its neighboring carbon. Whereas the F, yes, it's more electronegative, but it's a really short distance between the two nuclei. So it's more difficult for the F to leave than these over on this side of the series. And so that's why it's really important to understand the trends. Trends are very important. Okay. Just briefly talk about the mechanisms. For the SN2, we already went over this. The SN2 reactions primarily happen with those that are primary alkyl halides or methanol, like methanols in methyl halides, okay? They're bimolecular, that's what that 2 meant. So we have a nucleophilic substitution, and the rate-limiting step, there's 2 molecules. So that's where they get that this rate was equal to some little k times the original alkyl halide times whatever the nucleophile was. We talked about the transition state, that as one comes in, the other one is leaving. And so instead of it looking like a tetrahedral transition state, we actually have it where all of this is in the same plane. Okay, they kind of did it like the guillotine, where we have one hydrogen in the plane, one coming out towards us and one going away from us, whereas the nucleophile coming in and the leaving group leaving are in the plane of the paper here. So because of that, if you start, this one's not chiral, but if you started off with something that was chiral, you're going to get inversion. So if it started off with a chiral carbon that was 100% R, you're going to end up with something that's 100% S. Okay. The only exception to that would be is if, and it's very, very rare, but let's say that we had something that looked like this. Where whatever I'm trying to think, where whatever the nucleophile is, you already had one of those hang off of that carbon. Because it doesn't make sense. It's not going to be chiral in the final product because you're going to have 2 of the exact same things. Okay. So this is the reaction coordinate. We start off here. You always have to put energy into it. So there's always a transition state. And then we have our final product. It's much more simple than the SN1. Remember the SN1, we had the minima for the carbocation, which was higher than what you started off with. And then you ultimately got your final product there. This is just showing you color coordinating exactly what we talked about the inversion. Since it has to be a backside attack, because of that you get inversion. Like I said, the only way that it wouldn't be inverted is if, is this red or brown? Red. Is if we already had a red ball on here, then we'd have 2 red balls. So therefore it'd be achiral. But like I said, the odds of that happening are very rare. But it could happen. Mm-hmm.
Does inversion occur with other reactions aside from SN2?
You can, well, anytime that you're going to get some type of backside attack, you can get inversion. Okay, so the reason why is your book likes to talk about partial inversion, which I'm going to get to in just a moment. But I hate describing partial inversion because I like talking about it in the extremes. If you start off with in an SN2 reaction, if you start off with 100% of one enantiomer, you're going to get 100% of the other enantiomer. In your body, this happens a lot of times. You're either going to get retention of the stereoisomer, or you're going to get inversion. The reason why is we have enzymes that specifically restrict and make it to where the reaction can only occur on one side. So in vivo, it happens much more often than it would in vitro. Okay. Let me see, where are we? It shows all the little blobby parts. Okay, so steric, does anyone remember, what does it mean when we say something is steric? Steric hindrance, steric effects. It's like the fancy term for if something is sterically hindered. What does that mean? What is it? They talk about steric hindrance, steric strain, sterically challenged. I don't know, just steric in general. What is the big difference between these that you see here? You should be able to name this one. It's 2-bromo-2-methylpropane versus bromomethane. What's the big difference? This one has more steric hindrance or sterically restricted versus this one. So what's the big difference from it? Number of carbons, the size, right? The bulkiness, if you want to think of it as that way. So we're talking about how bulky it is. This is the ability for it to undergo SN2 reactions. Now so it's called steric hindrance. And remember, in order for an SN2 reaction, so let's say that this is our nucleophile. And I'm going to use the bromomethane first. Remember, it comes in from the backside, and as it's coming in, the bromine leaves, but it has to come in from the backside. Why does it make sense? Why is this one so slow to go SN2? Here's our nucleophile. La 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 la. What's the problem here? Pardon?
There's only one place you can go.
Like, it's hard to fit in. Remember, all of these, each one of these carbons has 3 hydrogens hanging off. It's in 3-dimensional space. So we're going to use, it's not faith integration, even though football many times is considered almost a religion in the South. It's football integration. So the problem here is, or one way if you want to think of it as football, is if this is the quarterback that you're trying to get a hold of or to attack or what have you, you can't get around. There's just too much there in order to get around there for it to happen, okay? So it's got a really good, I don't know if you want to consider an offensive line, but it's too hard to get into to do I shouldn't say the bromine's not the quarterback, this carbon's the quarterback, right? Because that's what's supposed to be attacked. There's just too much there for it to get around. Those are the big, bulky, Alabama offensive line there versus the Mighty Mites. I don't know. Do they even have Mighty Mite football here? Whatever that would be called here in Florida. That's like the 3rd graders that get together to play football. Okay, I'm not going to say that term. So we're going to call it Mighty Mites because that's what it's called back in the Ozarks. But if you can imagine a big 300-pound man nucleophile. The large 300-pound male nucleophile come up against 3, 9-year-old kids, it's going to be easy to do that backside attack and smack that carbon. Whereas if you've got that one 300-pound nucleophile man coming up against, well, they're not supposed to have 9 offensive linemen on there, but you have against 9 all along that, it's going to be much more difficult to hit that carbon. So This kind of interaction here, or this kind of setup here, is going to have to go SN1, right? It makes sense. The bromine's going to have to leave first. Plus, we already talked about the fact that that carbocation, whenever that happens, is more stable anyway because of due to induction and hyperconjugation, because it's got 3 friends to help it out, and that 3 friends have got, 9 hydrogens total to all help out. Whereas this one doesn't. It can't undergo SN1 because it can't form a stable carbocation. This one can. Okay. I used football. This is where they're starting to talk about, scientific terms. So the space occupied by the neighboring groups and causes like the bulkiness or whatever, that's a steric hindrance. So this is the likelihood of it going SN2. Opposite direction would be the likelihood of it going SN1. Okay, that's not written on there, but. Oh, okay. Need it whenever it gives me notifications. And then this is just a picture showing that same thing. We can see, what is that? We said that was red. Here we have our big old nucleophile coming in. It can smack that carbon. That would be the quarterback for football integration. That quarterback is not very well protected. Okay, this quarterback is a little bit more protected, but it's still not very well protected. That's the quarterback right there. And you can't even see that quarterback. It's on the inside. And you can barely see the leaving group. So that's why you can kind of get an idea. This is steric hindrance or steric crowding because it's well defended. And so it's going to be more likely or better for the bromine to leave first to form the carbocation than for the other to happen. And this should make sense. I know they give the fancy name, the neopentyl effect, but I told you I didn't expect you to memorize neopentyl. I wouldn't ask you that on something that you have to take in class, just because I don't want you to have to remember like all isobutyl, neopentyl, all those little special common names. All it means is even when you have a really big, bulky 1 carbon away, it can affect it. Now, if it's 2, 3, 4 carbons away, it has less of an effect. But you see here, this would be the quarterback in the football instance. And it's more difficult to get to it, to tack on the backside, just because we have a big, bulky person, or big, bulky groups right there. Okay? It just makes it less likely to do SN2 and more likely to do SN1, depending upon how close it is to big, bulky groups. All right.